In the previous video, we saw this graphic, which told us that in an electromagnetic wave, the E field and the B field components, which are vector fields, are always orthogonal to each other and mutually orthogonal to the direction of propagation. So, what we're doing in this video is investigating that a little bit further. So, because these are these are vector fields, they are subject to vector manipulation, just like any other vector quantity. So, let me introduce you to what's called the pointing vector, after I believe his name was Stephen Pointing, which is defined such that it is equal to 1 over mu naught E cross B. So the pointing vector is valuable for us. We're going to see in just a second that it gives us the intensity of the wave, but because this is a vector product, and you get a vector out of it, and notice the resultant vector has to be mutually orthogonal to the constituent vectors. What this gives you is the direction of the pointing vector is the direction of propagation for the wave itself. So if you're interested in, if you don't know which way the wave is traveling, but you know the E and B field component at some time, when they're both non-zero, you can determine the direction of propagation by examining the pointing vector. There are other things it does for us. Most importantly, if you look at the units here, what you will get, if you unpack all of the electric field and magnetic field units and magnetic permeability and put them all together, you get units of watts per square meter. That is intensity. What is intensity? Well, for a wave, intensity, the best I can explain it is to tell you that if it was a sound wave, intensity would have to do with loudness. A more intense wave is louder. For a flashlight, which is a type of electromagnetic wave, it would be brightness. The more intense flashlight would be brighter. So you can think of this as a measure. Brightness is not the right word because not all E and M waves are visible, but you can think of it as a measure of brightness, whatever that looks like for an X-ray. I don't know. It doesn't look like anything because you can't see them, but it's something analogous to that for visible light. It's intensity. It's the amount of power incident upon a particular area, right? It's power per square meter. Okay, so the E and B fields are both oscillating in time and space. More specifically, they are constantly changing and they're both zero at some point. And so the instantaneous value of the pointing vector turns out to be not particularly useful for us. What is useful for us is the time averaged value of the pointing vector, which can be given by several expressions, which I'm going to give you here. The intensity here is going to be, of the wave, is going to be given by the S average, which one way of expressing this is 1/2, which probably tells you that there was an averaging process, right? Specifically, we're averaging over a cosine function. Remember, the E and B fields are both trigonometric functions. The average of a cosine over one period is 1/2. The average of a sine over one period is 1/2. So there's clearly some sort of averaging process that goes into this. And then C, the speed of light, epsilon naught, E naught squared, where E naught is the maximum value of the electric field, right, which you can pick off from a written equation of the electric field component. So this is the time averaged pointing vector. It gives us the intensity of the wave, but of course, we don't have to express the E&M or the EM wave in terms of the electric field. I could express it in terms of the magnetic field. In that case, I'm going to get 1/2 C B naught squared over, already wrote the 2, mu naught. Again, 1/2 tells us there was an averaging process. I've got my magnetic constant here appearing with my magnetic field, just like my electric constant appeared with my electric field. Notice this is in the denominator where this is in the numerator. But you've seen something similar to that before when you saw the magnetic field due to a wire. Mu naught was in the numerator, whereas the electric field due to a point charge, it was in the denominator. So that's pretty standard. We can see these. So these are two different ways of expressing the time average Poynting vector that is the intensity of the field. Of course, I can combine these two to get a third expression, which is just this max, or I should say peak E field times peak B field over 2 mu naught will also give me the average time average Poynting vector. So which one of these you use depends on what you have, right? If you have the max E field, this is probably easiest. If you have the max B field, this is probably easiest. If you have both, knock yourself out. Use this one. I should point, it's a good exercise to try to derive this one from these two to get you started on that if you care to. Let me remind you that C is equal to E naught over B naught is also equal to 1 over root epsilon naught mu naught. You will use both of those in your derivation here if you so decide to do it, but it's a good exercise to go through to get here from both of these, but it's not required. But this is how we relate, or this is how the intensity comes out of the time averaged Poynting vector. You can do a lot more with this, but we're not going to in this class. If you are interested in this, by all means take sophomore level E&M and you will go through this a lot more. But for our class, this is really as far as I want you to go as far as familiarity with how to handle the waves. Of course, you are expected to be able to do cross products by this point. This could be fair game, but if you just need the average value, time averaged value, I should say, it's here.